good look. It's like that bad look of like you did something wrong.
Okay, so we're gonna finish up this finally after 3 days. Put this thing to rest. So
I'm thinking really hard.
I'm thinking you're really annoying to me.
I'm really glad that's on video. That's going down in history. We gotta get the culprit.
Second.
Okay, so let's talk about this last part where you have like the graph and you have to do all this stuff, right? So when you look at this one as opposed to like a horizontal motion, so you got this spring, it's oscillating back and forth. So here's the problem in terms of this overall value of U. Because of the fact that you're going to have gravitational potential energy, you have energy in the spring, like which one is it? I don't know. But here's the bigger idea, is that your total energy at any point is going to be some amount of kinetic energy plus some amount of potential energy. Okay, that's the bigger idea. And one option is that when it's at the middle, and then you have to get this concept in, that's at the middle, that's when you have your maximum kinetic energy, okay? So that kinetic energy is going to be 1/2 mv max squared, okay? So if you know what the velocity is in the middle, then you can figure out what that value is going to be. You can find that K max value. So here's kind of the process that goes through 21, 22, and 23. Okay? So I need you to understand how this works, because what you can physically measure. So how this played out is that you had a motion sensor down here, and it was sending a wave, sonic sound waves up, and it was bouncing off of the bottom of that, and it was sending a signal back, and it generated a graph. And so that graph that it generated was a position time graph that looked something like this, okay? And the bottom of that, like, is at 0.5, the top of that is about 1. So imagine that here's the sensor on the ground, okay? So when that thing is at the bottom of that oscillation, it's at 0.5 meters. Then when it's at the top of the oscillation, it goes up to 1. So it's oscillating between 0.5 and 1. Okay? So what that means is that total displacement is 0.5, which means your equilibrium point would be in the middle, which means it has a displacement or an amplitude of 0.25 meters on either side of that. Right? Now, this device also kept track of velocity. And that's what these sensors do. They can do position, and then it can do velocity at the same time. It's a cool deal. So your velocity time graph is starting at 0, and it's going like this. Okay? So up here, this spike up here is about 1.6 meters per second. Down here, that's at like negative 1.6 meters per second. Okay? So, if you look at what's happening, and this is where you have to be able to morph ideas between different graphs. So what we're saying is that this graph is starting at the bottom, okay? It's at 0.5. And I know that based upon the position time graph. It goes up to 1 meter. This is going from here up to 1. During that time, it has a positive velocity. So this system is defining upward as being a positive value. The other thing that you need to be able to do is correlate these two graphs at the same time. So when this velocity time graph has its maximum value of 1.6, if you look at what happens at 1.6, that's when that mass is going through that equilibrium point. So your maximum velocity on an oscillating spring is going to be when it's going through that equilibrium point. Now, the same thing is going to happen, and when we get to pendulum, this will make more sense. If you think about it, the pendulum does the same thing. As that pendulum goes back and forth, when is that pendulum going fastest? At the bottom, when it's at that equilibrium point. At any point past that, it's decreasing its kinetic energy because it's storing potential. So, a spring going up and down is, from an energy perspective, the same thing as a pendulum going back and forth. It's going to have its highest velocity either at the bottom of the pendulum swing or at the middle of the equilibrium point of that oscillation. Okay, that's what happens. So, you can have three potential types of energy: UG, KT, and US. Right? So, on 21, what we did is we said, okay, any potential energy that we could get would be E total minus some amount of kinetic energy. Right? So, there's two ways that we could find E total. One way is that we could use 1/2 K A squared, which is just a version of 1/2 kx squared, which is the energy stored in a spring. Or we could use 1/2 m v max squared. So this is where you look at the data that you have. Based upon the data that you were given in this problem, could you find E total setting it equal to 1/2 Ka squared? Can't do it. Why? What do you not have? You don't have the spring constant. Okay? You do not have the spring constant. Okay? You're not given the spring constant. So I can't do this. But I can look at the graph and I can find my Vmax. So I can find that total, that maximum kinetic energy, that E total, by using 1/2 mv max squared. Now, this is just going to be some of kinetic energy wherever that is. So this is the beauty of this problem. So if you look at the U equaling the E total, which is going to be 1/2 m v max squared minus 1/2 m some random velocity squared. Okay? So this is specific to the Vmax. That's when it's at the middle of the oscillation. This is just some other, could be any velocity. Now, think about this. If this is 0, okay, so this is the velocity at any point in the oscillation. Okay? This is important. This is the velocity at any point in the oscillation. If this is 0, what's U going to equal? That total. So when this is stopped, and where is it when it stopped? At the top or the bottom. So you don't have any kinetic energy. So when this goes to 0, that U value is going to be whatever the energy is in the system. Now, as soon as it starts to move, this is going to have some velocity. Now, think about this one. Let's go to the other extreme. What if this is also Vmax? Here's my Vmax, that's a fixed value. What if this is also Vmax? What's the value of my U? 0, because it's all existing as kinetic energy. Okay? So if this is anything else, the difference between those two is what energy you're storing as a value of U. So then you say, well, how do we get that velocity? Don't know, because if you look at that chart, you could look at the chart and kind of get an idea what the velocities are, but you've also been given that the velocity equals negative Vmax times the sine of 2 pi t over t. So all we did is that we took this and substituted that in for V. So that allows you to find the actual velocity at any point in the oscillation. Okay? Doesn't make any difference. As long as you know what little t is and you know what big T is, because you can look at the graph. What's the period? How long does it take to go from 0.5 back to 0.5? That's 1 second. Oh, cool. T is just 1 second. They couldn't have made it much easier than that. Okay? T is just 1 second. So then, knowing that and substituting that in, now I can find the velocity at any point. Okay? That's the main idea. So then on 23, all you're doing is just pulling that out, the common terms of 1/2 mv max squared, and then you have that equation left over. So on 24, you're finding the value of the potential energy at these different points, 0.25, 0.5, 0.75, and 1. Your answers are either going to be 0 or 0.16. Okay? Those are your only two options on 24. They're either going to be 0 or 0.16. Now, let's think about this. You're finding U. Okay? Finding U. So at time 0, what is the velocity at time 0? Look at your graph. What's the velocity at time 0? 0. So what is how is all of your energy existing?
Potential.
As potential. Okay? It's existing as potential energy. Now, at 0.25 seconds, look at 0.25 seconds. Okay? It's all kinetic because 0.25 seconds, where are you at? You're at, no, you're at the top. You're in the middle. So at 0.25 seconds, your value of U is going to be 0. You didn't even have to do any calculation. Oh, right, it's in the middle. It's all kinetic. Now, on the next page, over on 25, you're asked to graph the potential energy as a function of time. So that graph should look something like this. At time 0 is, because you're graphing potential energy, this is important, you're graphing potential energy, not kinetic. You're graphing potential energy. At time 0, is your potential energy going to be 0, or is it going to be 0.16? 0.16. So that's going to be 0.16 joules, because you're graphing potential energy. So obviously, what's it going to come down, right? It's going to go to 0, right? Now, is it ever going to go negative?
No.
No, because it's energy. It's a scalar quantity. Okay, it can't go negative. Okay? Right? Now, if you were asked to draw the kinetic energy versus time graph, what would that look like? Yeah, it'd be 180 degrees out of phase. Okay? So your potential or kinetic energy graph would look something like this. It'd be 180 degrees out of phase. Now, interesting thing happens. At some point, would the kinetic energy equal the potential energy?
Yes.
Yes.
Because it intersects.
Because those intersect. At some point, they're going to have the same numeric values.
You said no.
Someone said that.
Okay.
Wait, would that be
When
between
did I say
between
no?
it being stopped and
You were
between
listening
the
about
very
it.
bottom?
Just later, Gavin. Nobody said no.
Okay. So at some point, those energies can equal each other. And that's where those two lines cross. Okay? So when they cross, they have the same amount of energy. Okay, but that's only that point where they cross, where we're saying, oh, this is this intersection of these two types of energy. Okay. When you get to 27, using the information provided, determine the spring constant K. Okay? Okay. So that answer on 27 should be around 5. Whew. Okay?
Okay. How about 29?
Your answer to 29 should be around 10.
Like
It should be right.
Yeah.
Low side. Ish.
You didn't say.
Okay.
You didn't say.
So, period of oscillating gas is 5 times the square root of.
Mr. Birdcamp, can you
Oh,
explain
that
that
one.
Oh, that one.
You can't just say that.
In the mass, yeah, whatever.
No, Gavin, that's right.
Google also told me that.
That can't be the force. That's not force.
No,
What
it's not.
is
It's
it?
unfortunate. It's
I see. So,
Yeah.
Force is equal to the gravity. Equal to the gravity.
Oh, yeah.
He gave
No,
you
it's
four.
this
KX.
Wait, first net. Sorry. A times X. We have K, and we have X.
Yeah.
Okay, baby.
X is Well, that's
Why are we dividing by mass?
from the middle.
Now, on 29, 29 is going to boil down to F max, which is mass times acceleration. Okay? That's what you got. Now, at this point, you're going to be talking about your value being in terms of how far it's going to be stretched from the equilibrium position. Okay? This is going to be important. On 29, your F max, and I tell you this, assuming that is only a function of the spring. So how do you calculate a force generated by the spring?
Hook law.
Yes.
Hooke's law, Kx, right? So you just found the value of K. You just found that. Okay? You know what K is. You just found it. So the question being is, what are you going to use for X? You have one of two options.
Wait.
Are you going to use 0.5 or are you going to use 0.25? Why, Ms. Nelson?
Because in the middle, well, it's from 0.5 to 1, right?
Yeah.
So in the middle is 0.75, 0.75 at the top of the bottom is 0.25.
Yes.
I thought it was slowing
So
down.
X is going to be 0.25 because it's
How
the
did we not know
distance
that?
This point is
from
at
its
the bottom.
equilibrium point. Okay? Not the overall displacement. So you know what K is, you know what X is, and you know what the mass is.
Yeah, but this one's from the bottom.
Find the acceleration. So,
What was that?
Ah.
I don't. I'm confused.
Shannon, how did you phrase it when you asked me if I got a haircut? How did she phrase
You
that?
get a cut?
Oh, just a cut.
You get a cut?
Okay.
Yo, Ryan, I didn't know you got a haircut.
I noticed it. But I didn't say
It's
it.
slang.
You
It's
need to
slang.
be-
Am I even slang? Cut?
That's
That's fair.
Hey, cut is like
bro.
Okay, any other questions on that big lab? Now, let's talk about the multiple choice questions. Okay? So let's talk, yes?
What about 30?
Huh?
The graph?
Yeah? What about it?
Does it start from negative? Or positive?
No, it's going to start at positive.
Why?
Is there any?
Because here's the story. So if you look at your graph, if you go to your velocity time graph, it starts at 0, right?
Yeah.
And you're increasing positive velocity.
Oh. And it speeds up.
Showed this to her.
Okay, I thought it was slowing down for some
I don't
reason.
read instructions.
Because if you start with your velocity time graph,
Yeah.
your velocity time graph, look at this. What's the slope of the tangent lines on your velocity time graph? Are they positive or negative?
So how do you get that? Because I don't know.
So you used to change that. So the X is the displacement of the
I haven't.
Wait, so you said you wouldn't do that to us on the test, right? Where you like flip it around? So it'll look like this?
Right? That's a multiple choice acceleration.
He's gonna do that to us just once.
I don't know, I'm just gonna stay for a
Probably, I
little
swear. If he does that, I'm
How do you want to
throwing
stay?
hands.
Just chill out. We're not done. I'm not done yet.
We're gonna beef. He's gonna hear this when he watches this video later. Hyper can't.
Oh, I think it's clear. I think it's
That does not mean I don't have it. That means I gotta take it out later.
Yeah.
Instead of getting it in.
I knew that. For sure, for sure.
That's a bad thing.
Aw, dang it.
What, are we right?
This is for the first question.
Oh.
Yo, I don't think it's gonna be.
Sup, right?
Or just white.
Yeah.
White.
Because it's a pendulum. That's the equation for pendulum. I didn't either. Because this just says T sub P, but I looked on this one and it says pendulum.
See, what's the other equation shape?
Me too.
No, it's not bribery. What do you call it when you pay a Congress person?
Bribery?
No.
What's it called?
I feel like I should write
Yeah,
this.
they're lobbyists. He doesn't know what it is.
Oh, yeah, you know.
I'm trying to
Oh, we're not there yet.
It's gonna work, really.
I mean, it's like obvious, but like.
We're not making fun of the fact.
Okay.
Oh yeah, we never stopped.
All right.
We're all in.
So you do know?
Stop talking about APEC.
Yo, Gavin,
It's like Jewish law.
What?
They were talking about APEC. They were talking about APEC. How's that canceled?
Right, bro. We would never touch that.
What is this? Oh, this is.
Okay. So at this point, we have two different equations relating to the period either of a pendulum or the period of a spring. So a couple of things that are important in terms of what's in this equation and what is not in this equation. So all this is just the period of the pendulum. All I'm doing is just dimensional analysis showing you that the units work. You've got length, which is meters. You're dividing by the gravitational acceleration. You got meters per second squared. The m's cancel out. The second squared cancels out. Flips up. You get seconds. Okay? So if you look at this on the period of a pendulum, what are the only two things that determine the period of a pendulum? Period of a pendulum.
Nice.
Period
Length.
of a pendulum.
and
Length
I
and
don't think there is.
Gravity.
gravitational acceleration.
That would make
Okay? So here I have a rubber stopper on the end of this. Okay, and it's a certain length. Okay. If I took off the rubber stopper and put a much more massive 500 gram mass on the end of it, okay, what would that do to the period of the pendulum?
Make it bigger. Nada. There's no math.
Absolutely nothing.
Good job, Gavin.
Where can you put in the mass of the bob?
Nowhere.
You can't. Okay? This is for the period of the pendulum. Okay? Now, which is going to have a longer period? This, okay, or that? So which will have the longer period? This one
It's the same.
or this one? Why is it the same?
Where can you put that?
There's nowhere to put amplitude in the equation. Now, supposedly,
I'll say it for Wyatt.
I'm going to tap you like that in your forehead in just a second. Now, according to legend, how Galileo came up with this observation, according to legend, he was in a church that had, this is obviously well before lighting and electricity. So they had big chandeliers, they would have candles they would lit, okay? And supposedly there was a window open and it started, one of the candeliers started to swing. And Galileo was a little bit bored, so he used his pulse to time the period of the swing of the chandelier. And what he found was that, so there was this big wind, gust of wind, so it started to pretty big amplitude. And what he found is that even as that amplitude got smaller and smaller and smaller, just using his pulse on his wrist, he found that the period stayed the same. So according to the legend, that was how Galileo made that observation, was that he counted the pendulum swings.
Should we use that same
And then 2 times 2 is 4.
So, you go, so here's the beauty of this equation.
You know your answer.
Let's say that we lose all knowledge of physics. And we need to start over and we need to find the gravitational acceleration on the Earth. What's the easiest thing to do?
And the apple falls on her head.
Set up a pendulum. Okay?
I'm gonna calculate.
What was that?
You're not
Yo, get in an apple ball.
Yeah.
That is true.
Okay.
Yeah, so we're all floating around until that guy came around. Dude, I saw that on YouTube.
Alright, focus.
What am I saying?
Shaking too big. Forgive.
Now you get the devil.
I don't.
Hey, dude, like secretly, you
No.
are.
No.
You really do. You're just saying that.
No.
Yeah.
No.
Oh.
That time. This is not one of them. Okay. Now, so we could literally set up a pendulum. All we would have to know is the length of the pendulum. We measure the period. Boom. We can solve this for sure. So there you
I
go.
got the same thing,
Now, frequency and period are inverses of each other.
which is weird.
So if you want to look at, there's a couple of ways if you want to look like the frequency of the pendulum. One option is that you look at the period, and then you look at the impact that's going to have because it's the inverse of it. So if you make the pendulum longer, what happens to the value of t?
It increases.
It increases, it takes longer. So as the period gets longer, what's going to happen to the frequency? Go shorter. So if I have a really, really long pendulum, okay, as that goes back and forth, I'm not going to have that swing past very often. Now, if I have a short pendulum like this, okay, that's going to have a shorter value of t, but it's going to go have a higher frequency. So one option is that you just look at the relationship between frequency and period. If you're more of a mathematical person, you can take that equation for period and take the inverse of the whole thing. And you go, okay, so frequency is 1 over period. Well, that means that's going to be 1 over 2 pi, but then you also have to take the inverse of what's underneath the radical, because that's the only way that you can get 1 over seconds. So if you like, hey, I don't want to have to think through period and the impact on frequency, I just want to go straight to what's going to happen to frequency. So if you do that, you take the inverse of it, you go, okay, hey, I'm going to make the length longer. So if you look at how this is solved for frequency, and if you're dividing by L, as L gets bigger, what's going to happen to the frequency? It's going to get
Cancel.
smaller. So you could either think of it in terms of just keeping the period equation and look at the impact on frequency, or you could look at it in terms of solving for frequency. The same thing is going to be true for a spring. What are the only two things that determine the period of an oscillating spring? Mass and spring constant. Now, there is one assumption that is made on both of these. Obviously, if I do this and I'm not in a gravitational field and I try and set up a pendulum,
That would make no sense.
won't work. But you can still have the period of a spring. Obviously, oscillating vertically won't work because there's no gravitational field. But you can make it go back and forth horizontally. Okay, so you can still do springs and no gravitational field, but you can't do pendulums without a gravitational field. Okay, so on the multiple choice, so let me give you some hints. The most common answer you should have is B. Okay? I'm just telling you the most common answer is B. The second most common answer is C.
Wait, no, what?
Stop.
Get a load.
Gavin, what did you say?
I'm just telling you.
Hey, lock this in.
I'm not getting that many.
Hey, Mara, is that camera?
Hey.
Yeah.
Oh, you're going to jail.
Hey, he doesn't have eyes, bro. What are you talking about?
We're gonna.
Gavin, what did you say?
Hey, give it up, bro.
Okay. Make sure on question number 4 that you realize that there are 2 springs. Okay? So make sure you realize that there are 2 springs. Each one is carrying half the load. All right, anything else? No. Okay, so here's the sequence that I want. Basically, the sequence that we did it. I want the opening section, the purple section, the yellow, and then the graph on the back.
Opening, purple, yellow.
Hey,
Opening,
Nathan,
purple,
how'd
white,
you do
purple, yellow,
3?
graph.
What'd you get?
E.
D. I got D.
What'd you get on 1?
White, purple, yellow, graph.
Okay.
Did you get C or one?
I got C. I don't know how B is the most common. How's B the most common?